Good afternoon. My name is Kidira Malvo, and before you is Apex Tech. I would like to introduce the rest of the team members in their roles. Today we have Alex, who is the leader. We have the recorder, which is myself. Then we have the pessimist/optimist, Craig. And then we have the spokesperson, John. And then we also have the analyst, which is Tyreek. And today we would like to thank our sponsor, which is Northrop Grumman, and then our advisor, Dr. Shea. We will be presenting on the testing of high-power transistors, and that is our senior design proposal project. Our motivation for this project is to assist Northrop Grumman with evaluating high-power RF transistors. Then we would like to increase the knowledge to the body on LD-MOS and gallium nitride, and then of course high power RF transistors. We would like to do this by analyzing them through third-party evaluation. Now for a quick overview for our presentation, we will provide you with background information, and then we will also provide you with the requirements needed to develop our project. And then lastly, we will demonstrate and show you our proposed design. Now I would like to pass it on to my team lead, Alex.
Thank you very much, Karen. In preparation for continuing this project, we of course did a fair amount of background research, gathering various articles and patents and components as a component to how we were going to present and develop this project. The first one is a technical paper relating to the configuration of high-power RF transistors in use with short-band radar. This is a common application for high-power RF transistors. The relevant patent that we selected is a GaN high-power RF transistor. GaN, or gallium nitride, is one of a newer series of transistors developed because it is a higher power output than traditional LD-MOS or laterally diffuse metal oxide semiconductors, and is the most common version of high-power RF transistors currently used in the market. The relevant commercial part that we selected as an example is a test bench used to evaluate gallium nitride high-power RF transistors. It is different from the one that we propose to build, as it is meant for a specific series of technologies, whereas ours is meant to measure both LD-MOS and gallium nitride. It does a shorter range of bandwidth than ours does as well. We also are instructed to select a leftover component in our senior design lab. The original component we selected was an Arduino. However, upon further discussion with our advisor and with our project head, it was determined that the Arduino would not be compatible with our design. And so we determined instead to use an example, an NPN BJT, which we will demonstrate at the conclusion of this presentation. Now we're going to move on to the actual requirements of the board. At the most basic and highest level, the board is meant to test and verify high-power RF transistors. It must be able to do this on a range of bandwidths and on at least two types of RF transistors, gallium nitride and laterally diffuse MOS technologies. This is challenging, as connecting various types, despite connections being standardized, has various challenges in how you tune the board. The test board also must be able to record the inputs and the outputs of these transistors in order for later analysis and storage, as we intend to provide this information both to our sponsor and to the public at large. And now I'll pass this further discussion to my colleague, Tariq.
Another marketing requirement that we received from the customer was that the technologies utilized in our transistor test bench should be in compliance with government privacy policy. Apologize. A couple of the engineering requirements that we derive from this particular marketing requirement is that the transistor manufacturers have sales offices within the U.S. And then another engineering requirement that we derived from it was that the transistor manufacturers are Department of Defense accredited suppliers. Another marketing requirement received from the customer was that the test bench should be able to test gallium nitride and LD-MOS transistors. One of the engineering requirements we derive from this particular marketing requirement is that the test bench should be able to interface with at least two different types of high-power RF transistors. In particular, these two types are gallium nitride and the LD-MOS. Another or second engineering requirement we derive from this particular marketing requirement was that the test bench must be able to prevent damage to the connected transistor from overheating. The reasoning behind this particular engineering requirement is that these two given RF transistor technologies can reach particularly high temperatures, and so we need a way to basically prevent the transistor and the test bench from being damaged. And the final marketing requirement that we gathered from our customer was that the technologies utilized should be readily available and compatible. The first one, for this particular marketing requirement we got three engineering requirements out of it. The first one is that the transistors tested are standard in-stock products of Department of Defense accredited suppliers. The second engineering requirement is that the manufacturer still produces the transistors that we'll be testing in the test bench. And the last one is that the manufacturer will still be producing the transistor for the next 2 years. The reasoning behind these particular engineering requirements to fit or to meet this particular marketing requirement is that our goal here is to do a survey on the current technology transistor, RF high-powered transistor technology currently used in industry, and we don't want to use obsolete parts or parts that are basically at the end of their life. My colleague now, John, will be coming on to discuss our proposed design for our project.
Thank you, Tyree. As you can see, this is a block diagram at its barest, level 0, where we are just showing the current inputs and outputs that we expect from our test bench design. As you can see, the 4 inputs will be electrical current, the type of RF transistor, frequency ranges, and voltage. Our only output on this side will be real-time data, which we will export to a computer and use software to go over the various parameters that it's going to output there. So this is our functional requirements table, which is a fleshing out of the diagram. It's in explanation. It goes into further detail about each of the inputs and the output, what we'll be looking for, and the functionality of our design as a total. The inputs, as you can see, the electrical current will range from 100 milliamps to 5 amps pulsed. The RF transistor input will just select which type, be it, or it'll detect which type, be it gallium nitride or lateral diffusion MOSFET.
Yeah, but you also may have like a different size of each of the type for the transistors.
Yes, and we'll be able to detect that as well. And the frequency ranges we'll be looking for will be 1.03, 1.2 to 1.4 gigahertz, and 2.8 to 3.1 gigahertz. Our voltage input we'll be looking for 15 volts, minus 15 volts, and positive 50 volts. Now the output will output a lot of real-time data to the computer. We'll be monitoring the RF output power, DC to RF efficiency, gain variation, RF pulse width, input loss, and the harmonic and spurious generation specification. So as you can see, the functionality of our design total will be to safely test high-power RF transistors and then pass that generated data onto a storage device. The storage device we will then use a computer, something like that, to put the information into a spreadsheet and distribute that to Northrop Grumman. So in conclusion, We have similar designs and technologies that are going to be available that are going to help expedite our design process. There are software models out there already available so that we don't have to design every significant part from scratch, and we just need to input the different RF transistors that we're going to be using. The design will need to be compatible with a number of different technologies to meet the requirements, be they the gallium nitride, the LDMOS, and as well as the different brands, since we will be using a wide variety of different companies' products to test. The proposed design will also be able to test a variety of high-power RF transistors, but these test results will be recorded. They will be easily exportable to a spreadsheet. We will then pass this info on to Northrop Grumman, which they will have the ability to publish at their leisure. In conclusion, I want to turn this over to Craig and let him finish it.
Thank you, John. As you can see here, we have 3 references. The first reference is the relevant technical paper. Secondly, that is followed by the relevant patent. And lastly, we have a link to a Cree website in which that's one of the manufacturers of the RF power transistors that we may be using. Moving on to our demonstration, the purpose of the demonstration is to show the team's knowledge using the analog discovery device by measuring or analyzing data from their leftover part. As stated earlier in the presentation, the leftover part that we chose was an Arduino Uno, in which after further investigation and consideration, we found that would not be compatible with our project. So we chose to use an NPN BJT transistor, in which we will be using the analog discovery device to measure current. Unfortunately, the current through the BJT. Unfortunately, the current is not cannot be measured using the analog discovery natively. So we have 2 resistors in conjunction with the BJT, and which we will use the voltage of one of the resistors and use Ohm's law to find the current through the BJT. I will now move on to the next part of our demonstration, in which we go further into the specifications of our circuit.
As you can see here, as my colleague previously stated, we're using analog discovery to measure the voltage across a 5 kilo ohm resistor. This right here is on the collector side of the particular BJT, and we will be dividing the voltage that is recorded right here by that 5 kilo ohms in order to measure IC.
Then for the rest of the circuit, we have the 5 volts from the voltage source, which is connected to ground, and then which we have it connected to a resistor of 220 kilo ohms, which is connected, which right here, which shows the base. And then what we're trying to find is IB.
Thank you very much, Kadir. As you can see, first we calculated and then we measured to ensure that we knew all the values. We calculated IB to be 20 microamps, calculated IC as 0.47 milliamps, and then we calculated the beta using those 2 measurements. This fits and ensures that it is in operation for the BJT.
As you can see, according to our circuit diagram, we have a 12-volt power supply coming into the collector here, going through our 5K resistor. These are the leads for the analog discovery's oscilloscope. After the signal goes through here and we've measured the voltage across this resistor, it's going to go through this yellow wire into the collector. We have the base coming into the strip of this test board and out through the resistor here at the 220 kilo ohms. Lastly, this is the emitter leg. This is our ground coming out of that, which goes back to the ground on the power supply. Both supply voltages are grounded, and we expect to see about a 1.8 volt drop across the 5K resistor.
Okay, as stated before by my colleague John, we have the leads connected of the analog discovery across the resistor here, which is the 5K resistor. And using the analog discovery device and the software that comes with it called waveforms, we're using the oscilloscope section or portion. And as you can see, it's reading that voltage to be about 1.8-ish, I would say 1.8 volts. And you can use, well, I can stop it and freeze it so that you get a better view. And we can use the zoom feature here to zoom in on a portion of the wave. And you just click on it, and as you can see there, it's about 1.8 volts.
So, thank you for the demonstration. And just one question is how do you make sure that's in saturation condition of the bipolar?
Oh, you need to find two different values in order to make sure that it is in saturation. The first is that IC must exceed 0.3 millivolts.
Right.
Yeah.
Okay.
And the second condition being that IB is, VCE must be,
Your VCE must be above
Above.
0.2.
yeah,
0.7 volt. Right?
yeah, 0.7
You mean-
volts.
you mean
Yeah.
Yes.
Yeah, that's the 0.7.
Mm-hmm.
Okay. Yeah. So just make sure VCE is bigger than 0.3 or
0.3.
something like that.
Yeah,
Okay.
must be bigger than 0.3,
Mhm.
right there,
To get it. Okay.
and then, yeah, and 0.7.
So just make sure by doing the circuit stuff to get the series stuff understand completely. So
Mhm.
thank you for your demonstration. No more questions.
Okay.
Thank you, Dr. Chen.
Thanks.